Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, layout diagrams using CMOS design style. In our previous topic, we have completed the layout diagrams using the NMOS design style, where we have taken the lambda based design rules of which will be helpful in drawing the layout diagrams, and then we have extended our discussion to few of the examples. Presently, we will look into the layout diagrams of CMOS design based on CMOS design. After completion of this lecture, you will be able to illustrate the lambda based design rules of CMOS, and you will be able to develop the layout diagrams using CMOS design. This has been taken in our previous lecture also, the basic MOSFET structure, how it looks like. In order to draw a layout, we need to visualize the device structure from its top view. This is the top view. So when you see it to the top view, so this is the source and this is the drain. So like this forms the source and drain, and this forms the gate. So this represents the source and this represents the drain, and this portion represents the gate, that is polysilicon. And this dimension is the length of the channel, and perpendicular dimension, this is the width of the channel. Going into the details, in a CMOS device, pull-up network will be of PMOS transistors, pull-down network will be of NMOS transistors. So always a pull-up network and a pull-down network for a CMOS, right, where the inputs will be given to the short-circuited gates and outputs will be taken from the short-circuited drain, and pull-up network connected to the supply and pull-down network connected to the ground. The channel mobility of electrons is approximately twice that of holes, which is known to us. Conductivity of NMOS, hence what happens, conductivity of NMOS is twice that of PMOS. But in case of CMOS inverters, one of the devices is always switched off. So we know already, based on the input given, as pull-up and pull-down are complementary transistors, for the same applied input at the gate, if pull-up is in on state, pull-down will be in off state, and vice versa, and has very high impedance for the switched off transistor. So that is what the noise margin is very large in CMOS circuits compared to an NMOS. In turn, the aspect ratio for CMOS is 1:1. Pull-up and pull-down, ZPU by ZPD ratio, that is inverter ratio, is 1:1. That is length to width ratio of a pull-up network and length to width ratio of pull-down network is going to be same. As one of the devices always of 1:1 inverter ratio gives a more symmetric layout. Few design rules for CMOS: line size and spacing. For metal, minimum width is 3 lambda. This is similar to NMOS, and spacing is 3 lambda. For metal 2, minimum width is 3 lambda, whereas spacing is 4 lambda. For polysilicon, this is again similar to NMOS, 2 lambda width and 2 lambda spacing. And as for diffusion, this has changed to 3 lambda width and 3 lambda spacing, whereas for NMOS that would be 2 lambda and 2 lambda. Whereas here we have a term called well in CMOS design, as we all know during CMOS fabrication what is meant by a well, which is not present in NMOS fabrication. So minimum width of the well should be 6 lambda, whereas minimum N well and P well space is 6 lambda, and if they are at same potential, that is at 6 lambda, and if they are at different potential, that should be 9 lambda. And whereas in CMOS design, the transistors minimum width should be 3 lambda and minimum length should be 2 lambda. So if I have a transistor overlap with polysilicon and diffusion, let us say this is diffusion and this is polysilicon, so this forms the length of the channel and this forms the width of the channel. So width of the channel should be minimum of 3 lambda and this length should be 2 lambda. So minimum poly overhang should be 2 lambda. Poly overhang means this one. Beyond the diffusion, how much the poly should extend, that should be 2 lambda. Whereas contacts and vias, they should be of size 2 lambda by 2 lambda, and separation between the cuts of the contact should be minimum 2 lambda, and overlap, as I mentioned, for the contact cuts should be 1 lambda in all directions. So we have a basic CMOS inverter layout in CMOS design. So all of us know the basic structure of a CMOS device, how it looks like. Just redrawing it for our easiness. So here the input will be applied, and here the output will be collected, and where this source is connected to supply and this source is connected to ground. Drain short circuited, we take the output, gate short circuited, that is the input, and this is the PMOS device, and this is the NMOS device. See here, the procedure for drawing is first you are going to draw this metal rails for supply and the ground. So this is the supply and this is the ground metal layer. Go back. So this is the ground metal layer, and then what should be done is, see here, this is a polysilicon which is running throughout the layout, this poly, and see this yellow one is the P diffusion, where now this side it is forming the source and this side it is forming the drain, and this one represents your channel length and this one represents your channel width. And similarly here we have this poly, so this forms a PMOS transistor now, poly overlapping the P diffusion. Now here this is poly, this is overlapping, this is N diffusion, green color coding, N diffusion, this is overlap will form the transistor similarly. So this is an NMOS transistor. Now see both the PMOS and NMOS transistors, how they are connected. See the drains, this is the drain region and this is the drain region. Both of them are connected through a metal using contacts, and the output is taken here, that is Y. And whereas input is applied to the polysilicon where both the gates are connected. This is A, input A. So this is a color code based layout, and its equivalent grayscale layout is shown here for your reference. You can go through this one. Then comes a CMOS NAND gate, where you know once you need to draw its circuit schematic of CMOS NAND gate, how it will look like. So whereas in the pull down network, NAND gate means both the NMOS transistors will be in series. So in turn the PMOS transistors should be in parallel in the pull up network, and this forms your output. So for this one, if you draw the layout, color code based layout, this will be the representation, and for gray code this is the representation. And then comes a CMOS NOR gate. So similar to CMOS NAND gate, in the pull down network of CMOS NOR gate, we have two NMOS transistors connected in parallel. So when two NMOS transistors are connected in parallel in the pull down, so that is obvious. In the pull up, two PMOS transistors will be connected in series. So for this representation, what is the layout diagram is represented here using color layout coding, and this one is grayscale coding layout. Right? Hope this is clear. So you can solve as many examples as possible, and few lecture level questions have been presented here for your practice. That's all for this topic. Thank you. Happy learning.